Okay, so what we're doing here, we're solving the electric field for the quadrupole. That's what we're doing here. Okay, so we did for the dipole. Note see that the equation for the dipole is in the electric field for the equation of the dipole is inversely proportional to the cube of the distance. Recall that for the electric monopole or a single charge, the electric field is the inverse of the square of the distance, right? And then what about the quadrupole? What that is going to be? Okay, so we're going to build here an electric quadrupole. We start with the x and y axis. We're going to put a positive charge on the right side, a positive charge on the left side in this x and y axis. And on the top of that, we're going to add a negative charge to the origin that is equal to minus 2q. In this specific case, the net charge of the system is going to be 0, just like the electric dipole, minus 2q plus q plus q. Okay? And why is it an electric quadrupole? Well, it's considered an electric quadrupole because the electric dipole moment, okay, let's put it, electric dipole moment vector is equal to 0. Is equal to 0. We have an electric dipole moment to the left, another electric dipole moment to the right. You sum this vector to this one, and we get a 0 value. Okay? And now what we're going to do next, we are going to calculate the electric field of this electric charge distribution. Okay, so let's get that at a given position y. Let me get this y. Yeah, the y stays here. And I'm going to take advantage of the, here you go, I'm going to take advantage of this drawing here that I already have for the electric dipole. Okay, so here you go. The electric field of the positive charge is, it's in this direction, to the right at an angle, right? The electric field for the other charge here on the right is going to be to the left, like that. That should be the left charge, not the right one. Those electric fields should have the same magnitude because that point is the same distance. Left. Okay. And then we have an electric field due to this major charge here that is going to be pointing downward, and it should be a larger factor because the charge is bigger and also the point's closer to that charge. I'm going to get this in a different color and a different size as well. Here you go. Middle. E left, E right, E middle. Like that. Where's it? Here's the left, right? What? Yeah, that's the right charge, right? The charge on the right. Huh? E left. Are you talking about this one here? Yeah, the E left is the electric field of the left charge. Okay, see, that's the left charge, right? Let me do it. Let me see. Oh, yeah, this one here needs to be relabeled. Here you go. See that? That's the electric field of this charge here, the charge on the left. I'm calling it electric field of the left charge. It's a matter of notation. Make sense? Electric field of the left charge, right? Left charge, right charge. Does it answer your question? Okay? It's a matter of notation. And then, electric field of the right charge, right? And then the electric field of the middle charge. Okay? Let's work out the net electric field of this charge distribution. And let's see what we get. From this distribution, it looks like that the net field is going to be, it looks like the net, from this, just using this qualitative approach, you can picture that the net electric field is going to be something like that. Okay? Net electric field is going to be something like that. Because the left and the right electric field has only a y component upward, right? Just from this nice qualitative approach, you can come up with a qualitative answer. So it's a field that goes downwards. But now we are going to do mathematically, step by step. Okay? We're going to do that mathematically, step by step. Here you go. Start with this one. Go to the notes, quadrupole. E field of a quadrupole. Of an electric quadrupole. Okay, so here you go. I'm gonna take advantage of this equation for the dipole, but I'm gonna relabel it right, left, right, and a third electric charge. It's gonna be the middle one. Mid. Otherwise the notation becomes too awkward, right? The left charge is going to have an electric field that is like that. The right charge is going to have an electric field that is like that. And the mid charge is going to have an electric field that is like that. The distance is going to be y squared. Oops. What the heck is going on? Okay, now we got it. Okay. And there is no term like that. Oh, don't forget the y hat. Okay. Go ahead, practice this derivation. This is very good exercise. It looks like awkward, but it's a very good exercise for understanding what's going on. Okay, so this negative component, this x component here, is going to cancel out with this other x component, right? So, right? And you're going to have only a y component. I'm going to make it look nice. Okay. Next step is going to be twice that, because those two components are exactly the same. And now we go the next step. We're gonna simplify as much as we can. Okay, what can we do? We can put this term plus this term in evidence. Okay, so let's see, 2kq 2kq y hat. Okay, we go is something like that. Like that. Let's go the next step. We are going to, okay, so this sign, and that, let's see, let's go get the y that there. Let's put under the same denominator first. Okay, we go. We go, this one. This one goes here upstairs. This one goes here upstairs. Combine the two terms, we get something like that. I don't need this parenthesis, right? So let's see if I can. I'm gonna get the sign too. I'm going to here write it. We're gonna here write the sign. The sign of theta is this angle right in here. Sine of theta is going to be this angle here as well. It's going to be y divided by this length. Y divided by this length right in here. Okay, so next step, we go. Y divided by the square root of this term. Square root right in here. Like that. Okay. What else can we do about that? What else can you do about that? Okay, there's one more thing we can do about that. We are going, it's, what needs to be done here? Right now we cannot see exactly what's going on, okay? But in order to see exactly what's going on, what we have to do? We have to go back to this term here, to this relation here, and make an approximation. Okay, so let's make an approximation. Okay, going back to the previous relation. Don't forget that's the total. To this previous relation here. So notice that thing is starting to get complicated, right? So when you start to see something like that complicated into the equation, you know, it's difficult to understand what's going on. So when you start seeing something complicated like that, you take a break, you know, and see if you can do something better elsewhere, right? And that's what I'm going to do right now. Okay, go back to this relation, right? Do the substitution that we did. Here you go. Here's the substitution right in here. Okay, we're gonna do another term here. Go. This term is gonna go downstairs. When it goes downstairs, becomes 3/2, like that, right? Here you go. And now we do an approximation for y much greater than a. Sometimes we have to do the approximation. In this case, we have to. Okay, and you're going to see an interesting result. Okay, when you have, how do you perform this approximation for y much greater than a, right? The trick, the mathematical trick is the following. You put the a, let's see, you put the y in evidence, the y squared in evidence, only the left term. You don't have to worry about the right term because we don't have any a's here, right? Let's see, we gotta get the bracket. Okay, here you go. I'm putting the y squared in evidence. When I put the y squared in evidence, the term with the a squared gets the y squared divided there. Make sense? I didn't do the approximation yet. This is not an approximation. What's going to come next is the approximation. Oh, wait a minute, not yet. I'm going to do one more thing here. Okay, what I'm going to do, I'm going to take this guy out of the parentheses. When I take this guy out of the square root that you have there, it becomes y to the cube, right? And now we apply the approximation. There is an important approximation in mathematics that we call the binomial approximation. I'm going to write that down here. Using the binomial approximation for the first term, we get, oh, before doing the binomial approximation, we also have, yeah, we get, we're going to do a binomial approximation. Don't forget that we still can have a cancellation here, right? Here you go. I can cancel. Let's do this one first. That is easy to do. Okay, and now we do the binomial approximation. Every time that we have an approximation, we have to use that special sign of the approximation. You don't use the regular equal sign, right? You use the approximation sign. So here go. Get this guy here. Paste it here, right? And I'm gonna even do something else too. I'm gonna get this y square in evidence, okay? We have 1 divided by a y square here, 1 divided by y square here, right? So I'm gonna do that here. Here you go. So it becomes more obvious what your approximation is going to be. Here you go. Now I don't need this y square anymore. Okay. Can I do better than that? Make it look cleaner? Yes, I can make it look cleaner. Eliminate one of the parentheses. We didn't need the parentheses here either, right? Let's see. We didn't need the parentheses here either. So make it look nicer. For now, it's still an equality, right? Let me put the equality back, and now I'm going to use the approximation. Everybody knows the binomial approximation? Okay. If y is much greater than a, this term here is almost 0, right? Right? Okay. If y, here you go. I want to write that down here for you. So we have documented. If y is much greater than a, okay, the first term between parentheses is almost 0. Okay. So to say that this guy here is approximately 0, is approximately 0, to say that, it may work at times and may not work at times, okay? To say it is equal to 0 may work. No, sorry, not 0, approximately 1, right? Because this guy here is 0. May work at times, but it may not work at other times. For this approximation that you see here, under this equation here, doesn't work. And I'm going to show you why it doesn't work. This approximation, the above approximation does not work for the electric field equation. Why is that? For the following reason. When we apply it, what happens to the electric field? When we apply this approximation, what happens to the electric field of the quadrupole? Huh? Become equal to what? Yeah, it becomes equal to 0, right? That's what we call the trivial solution. Okay? So nobody likes to use nobody wants to have a trivial solution. We always want to have a solution that's non-trivial. So in order to get the non-trivial solution, we have to come up with the binomial approximation. We have to use the binomial approximation here in this relation. So instead of saying that 1 divided by this guy here is 1, we're going to go the next term. Okay? So the binomial approximation instead, okay? If we use the binomial approximation, we have, it's going to be something like that, minus. This thing is just like a Taylor series expansion, okay? That's what this thing is. That's what the binomial approximation is. A Taylor series expansion up to this term right in here. Okay? Have you ever seen that? Here you go. Okay, 1 divided 1 plus x, right? I'm gonna here write it in a different way so you might recognize, okay? It's gonna be 1 plus x, okay? 1 plus x is going to be equal to, like that. 4x much less than 1. That's what we did, okay? So now using this approximation, we are going to end up getting a non-zero electric field. Okay, so here you go. I'm gonna substitute that right in here. Here you go. My let's see. I want yeah, I can use this one instead. Better. Okay, and we go ahead substitute my 1 for this term here. Okay. What we did here, what we did here is called the zero order approximation, which sometimes works, sometimes doesn't work, depending on the equation that you're dealing with. What we have here is not the zero order approximation, it's the second order approximation because we have a square here. Okay? So when we go ahead apply this relationship, we get a non-zero electric field. This is a very nice trick in math. This one ends up canceling, yes. And this also ends up canceling just like before, but not the final electric field. The final electric field that ends up being equal to a value that is non-trivial. Okay, so here you go. Let's finish. This 2 cancels out this 2. This y square combines with this square. Okay, becomes force power. Yeah, I cancel out this one here, this 2 here. And this 3, I'm gonna put it here. Goes right in here. The y square goes away, right? The 3 goes away. And then we have this a square right in here. And now we start to see a pattern. Notice that the electric field is negative, right? Just like we had predicted in our drawing of the electric quadrupole. Just like we had predicted in the drawing of the electric quadrupole. So now I want to put side by side all those equations that we derived. I'm going to put it here. Here you go. Quadrupole. Quadrupole. And I'm going to do the following. I'm going to say that it's proportional. And I'm going to use the magnitude so to make it simple. So you can see the pattern that we get. This one here. Here you go. The magnitude. So I can also get rid of this guy. Okay. And you don't have to keep on carrying negative values. For the electric quadrupole, the electric field is a constant. QA squared K is a constant, right? Let's see. Put it quad. C quadrupole divided by y to the fourth power. Okay? That's what we got here. Let's not, here you go. For an electric Monopole, you already have that by heart, right? Is going to be a constant divided by a square, the square of the distance. And I'm going to put it here, monopole. Yeah. And for an electric dipole, let's put here monopole. For an electric dipole, here is not an approximation, here is an exact solution, right? For an electric dipole, okay, it's going to be what? A Q dipole divided by y to the third power. And for a quadrupole, we just saw that is the fourth power. This relation that applies to the most generic case. And because it applies to the most generic case, I'm gonna even put here, r square, the distance square, the distance cube, and the distance to the fourth power. Okay? And if you go to the octupole, it's gonna be r to the fifth. Or you go to the next one, it's gonna be r to the sixth, and so on. Okay? You can even go back here to the equations that we did for the dipole. Where's the equation for the dipole that we did last time? Here you go. Right in here. Okay? What you see right in here is the cube of the distance. Yes, it is the cube of the distance. Why is that? You have this a term that is squared, and this term is raised to the power of 3/2. A square plus r square is r square. Okay? Here you go. Let me write that again. At large distances, right? At large distance become r square. The r square raised to 3/2 of power becomes r to the cube. Okay? I didn't do the approximation here, but if you do the approximation, that's what you get. Okay? Got the idea? So it's a pattern that we have. So for every electric charge distribution that we have out there, okay? Very important. For every electric charge distribution we have out there, the electric field will be a combination for any genetic electric charge distribution you have out there. The electric field will be a combination of the electric field of a point charge, which you also call a monopole, will be a linear combination E field of a dipole, the E field of a quadrupole, etc. Let me write that down. For any electric field E, for any E field E, we have E field. For any genetic field E, we have, we go, let's write this one like that. Can you remember that? Genetic, I'm gonna put genetic. This is going to be a linear combination of those terms. And we have another term. It's possible to prove that, but we're not gonna do that. Plus whatever. And then you have an octopole, and then a 16th pole, 32 pole, and so on. Okay? So that's what we have. It's 5:45 right now. Let me get a pause here. And so we are going to go to the next step now. Let me explain what we did so far. So far, we have calculated the electric field of a distribution of point charges. Okay. The next step now is to determine the E field of a continuous distribution of charges. Not point charges, not point charges, but a finite distribution of charges. Okay, finite distribution of charges mean, can be a linear distribution of charges, like a line with electric charges very close to each other. It can be a two-dimensional distribution of a charge, like a disk. That's a two-dimensional charge, right? A disk. And can be also a solid sphere. A solid sphere with charges distribution in the volume of the charge, in the volume of the sphere. There you go. So let's go down here. See if I can have an illustration here for you. Yeah, here you go. Yeah, we did just point charges, right? Here you go. Here's the case of a point charge, point charge distribution, Q1 and Q2. Okay, the electric field of 1, the electric field of 2. That all you gotta do is to do that equation for the point charges and combine them vectorially. When we have a continuous distribution of charges, like this one that you see right in here, okay, this situation is more difficult to calculate. It's different. We want to calculate the electric field at this point. Okay. So how do you treat this type of charge distribution? Okay. Well, you treat this charge distribution as though it is made up of several infinitesimal point charges. So let's say a charge that here at this spot will contribute an electric field at this position right here. Okay? And it will have this electric field right here, electric field 1. Another charge that I call it Q2 at this spot will have another electric field contribution that's going to be something like that. And so on. Okay? So that's the qualitative idea of how to solve this problem. Each of those infinitesimal regions in the continuous charge distribution behaves like a point charge. Okay? So mathematically speaking, how do we characterize it? We characterize it in this way. Okay? Remember the point charge is kq over r squared? So the electric field of a point charge is kq r squared r hat, right? Okay, the infinitesimal charge contribution in a volume of charge is going to be given by k dq r squared. And then all you have to do is to integrate this equation to find the net field contribution of that distribution. Okay, and there are a few. There's some neat techniques that we can use to make it easier for us to calculate this integral. Okay, so let's write that down here for you in the notes. Right. Okay. So how do we calculate the net field of a continuous distribution of charges. Okay, we treat the continuous distribution as made up of several infinitesimal charges closely spaced. Or okay, so it's gonna be, you go, it's gonna be like a differential electric field. Okay, k dq over r square in the r hat direction. The tricky part is this r hat. But I'm gonna show you how to calculate those. You go. The tricky part is this r hat, okay? To make it easier for you to solve this type of problems, we should be divided into 3 different problems of increasing difficulty, okay? We start with the easiest one, okay? So first, we're going to solve for the electric field, the field of a linear charge distribution, 1D charge distribution. Now you should know what should come next, right? Then, first, we'll solve for the field of a linear charge distribution, 1D charge. Then, next, it's the field of a surface charge distribution, 2D. And last, we solve for the electric field of a volumetric charge distribution, 3D. And what is the trick to solve each one of them? Okay. The trick to solve each one of them is to write the Q in a special format. Okay? This is the Q that you see here. For 1D charge distribution, one-dimensional charge distribution, we define the linear density, charge distribution that we call lambda. How is this linear charge distribution defined? Okay. By the same token that we define a linear mass density, recall how we defined a linear mass density in physics 37. Okay? How do we define that? Remember that? We also use the letter lambda to lambda. But how do we define it? We define that as being dm divided by what? Dx, right? Remember that? And I'm gonna put here a subscript m just to differentiate it from the charge distribution. Remember that? A linear charge density, linear charge density. I just define linear charge density, not a linear density. Linear charge density lambda. Here we go. A linear charge density lambda we define the same way, but replacing the m with the charge q. That's a really nice trick that works very well. Okay. No, because it's a linear charge distribution, right? It's one dimensional. And we can put the one dimension in the x-axis, right? Okay, so the next step should be what? The next step would be to write the q in terms of lambda dx. Right, so here you go. Dx. Like that, right? Here you go. Remember, we're doing the easiest of all problems out there. One-dimensional charge distribution. Substitute that right in here. And look for possible solutions. Here you go. Here you go. We are not going to do the most generic solution of those charges. We're going to do a simpler types of solution, okay? So let me see if I have an illustration for you here. Yeah, this one. Okay? So we start with this one right in here. Then we go to this one here, okay? This one is a little bit more difficult. Although mathematically simpler, but visually it's more difficult to visualize. Let's start with this one here that's a linear charge distribution. You start, you know, start with a linear charge distribution of a linear charge distribution of linear charge. Let's see. Start with a linear charge distribution. Linear uniform charge distribution. Uniform charge distribution, like that. And what does it mean, uniform charge distribution? See, that's the samples of problems that you're going to see out there. Linear uniform charge distribution. What does it mean, linear uniform charge distribution? It means that the amount of electric charge in a small dx here is equal to the same amount of charge in another small dx here and another small dx here. You know, the linear charge distribution is not a function of position. That's what it means. Okay? So what does it mean? This means that lambda is, uniform. Uniform means does not depend on position. An easier way to state that is to say that lambda is constant, is equal to a constant value, or uniform, okay? We use the definition of constant for one thing and the definition of uniform for something else, okay? So let me give you an example, right? Start with a uniform charge distribution of net charge Q and length L. Okay? And by uniform, what does it mean? It means that lambda is constant, and because it's constant, the lambda is going to be Q divided by L. Make sense? Okay? That's the simplest type of problem that you're going to see out there for 1D distribution. Not the simplest, I would say the second simplest. So let's take a look at this guy here. Here you go. We have this charge position, this left side of the rod. It's a rod position at A. It is one dimensional. By one dimensional, what do we mean? We mean that the length of the rod is at least 10 times the diameter of the rod. Okay. And what do we want to do? We want to calculate the electric field at the origin of this xy axis. I'm not calculating the electric field in the whole space. Calculating the electric field in the whole space is a far more difficult problem. It's possible to do that analytically, but it's going to be a, loss of work. Okay? So let's do something simpler. Find the net electric field at this point, at the origin of the axis. Do you see my infinitesimal charge right in here? I illustrated as this square here. This infinitesimal charge is providing a infinitesimal electric field here at this spot. Then we have another infinitesimal charge here that I'm calling dq2, which, by the way, has the same amount of charge as this one because the rod is uniform. Okay, that's going to contribute another electric field, another infinitesimal electric field, which is going to be slightly greater than this one because it's closer, right? Make sense? It's closer. And so on. You have a bunch more of charges in there. Okay, so here you go. What did I do here? Yeah. Okay, so how do we treat this problem? Okay, this guy here I'm calling the x-axis. But the position of the infinitesimal charge I call the x prime. Picture that? Okay? The position in the space, in this axis, here we call x. But the position of the charge, we call it x prime. Okay? X prime 1, x prime 2, x prime 3, so on. Okay, so here you go. One of those x prime, right? And then we're going to, how do we do that? Again, we are doing only here, calculating only here this spot, right? If you were to calculate another spot, it's going to be more difficult. At this point here, all the electric fields are contributing, all the electric charges are contributing an electric field to the left. And by the way, I gotta tell you that this net charge is greater than 0, okay? If the field is in that direction, it means that the net charge greater than 0. And lambda 2 is greater than 0, which implies that lambda 2 is greater than 0. Okay, so let's go ahead and work this solution. Here you go. From that simple investigation, right, that we did, we can say that the infinitesimal electric field contribution is going to be given by Q over L dx. And by the way, the right way to do that would be to put x prime, because we are integrating only along the position of the where we have charges. Okay, and the r square is the distance of the infinitesimal charge to that point that I also call x prime, which should be squared. Looking at the drawing, we see that no matter which charge we're dealing with, this electric field contribution will always be in the minus x hat direction, right? Just by taking a look at that. So here, instead of x r hat, now I'm going to write down an x hat with a minus sign. Here you go, like that. And now we have to figure out how to solve this problem. We will have, we go, let's see what we have to do. I'm gonna simplify, right? And I'll put the negative here, and we go. And now I'm gonna do even, make it look even nicer. I'm gonna put it right in here outside. And what do I have to do next? I have to integrate. I have to integrate this. This is like a differential equation, right? A total differential equation. Here we go. Let's put the, I'm gonna put everything within an integral. Here we go. Okay, that's the integral. Let's take a look at our drawing again. Let's see what are the limits of integration. The limits of integration is from a until a plus L, right? Is that large enough for you to see, folks? Right, that's the limit of integration. So I'm gonna write that down. X prime is from a to a plus L. What else can we do here? I'm gonna put everything here under the parentheses just to give you a hard time. Okay, I want you to tell me what is constant and what is not constant, right? There are those, the negative sign is obvious that it's constant, so I put it outside the integral. And I don't need that anymore. Okay, don't need that anymore. Tell me what's constant and what is not constant. What can I take out of the integral? What I cannot take out of the integral? Is this guy constant? Okay. Okay, so let's take it out. Is Q constant? Is L constant? Okay, so let me take them out. Now the tricky one. What about the x hat? Is it constant or not? It's a vector. Is it constant or not? That's the question that you have to ask yourself. Okay? Nobody can. It looks like it. Can you picture that? Try to picture that. I'm going to integrate from A to L plus to A plus L. The electric field is going to point to the left side of this spot. Okay? When I integrate from here exactly at the tip, the electric field is still going to point to the minus x hat direction. Does the x hat change the direction? That's the question that you have to ask yourself. Here you go. Here you go. Here's my x hat, right? I'm going to put it a little bit shorter. Does the x hat change direction as I integrate from this tip to the other tip of the rod? No, right? X hat and y hat and z hat, they are constant vectors. You know, when you do integration in space, they remain constant. Make sense? Okay? So let's go to our drawing. Now I can take this one out, sure, of the integral. And I'm going to simplify my integral. Make it look like that. And we are now at a point that we can solve our problem, right? So, what is this integral here? That's easy, right? You know that, right? What's that? X prime to the cube, right? No, it's not to the cube. It's to the first power. And then what else? I gotta put a negative sign as well. Wait a minute, wait a minute. Oh no, yeah, that's right. Put here a parenthesis. And we put the negative sign in front of, right? When we differentiate minus 1 over x prime, we get plus 1 of 1 over x prime square, right? And then we can apply the limits as well. It's gonna be a plus L. And I don't need this integral anymore. Let's continue with our derivation. I'm gonna cancel out this negative sign in the next step, and then I will finally apply the limit. Let's not forget that we are dealing with a limit in x prime. Here we go. Here we go. A plus L, right? Oops. Yeah, that's good. L. No, it's not L, it's A. Okay, and I don't need the limits anymore. Like that. Okay, so can we do something else? Let's see if we can do something else. We keep on deriving until it becomes simpler, okay? If it becomes more complicated, the next step, then, don't go the next step. So we gotta put the same denominator. Sometimes we know that's gonna turn out simpler, but sometimes we don't know, and it's just a matter of trial and error. Here you go. I put this one, A goes upstairs. I put this one right in here, A plus L goes upstairs. Okay. Can we get simpler than that? Let's see if we can. Yeah, it looks like we can get simpler than that. Now they have the same denominator, and see, we have a negative sign here, and this A is going to cancel out with this A. See that? Right? It's going to cancel out. So I'm going to, here go, take this one out here, negative, here go. Next step, A cancel out with minus A. And remember from our observation in the drawing, the net field here must end up being to the negative side of x, right? If it doesn't end up to the negative side of x in our derivation, that must be because we did some mistake. Are we getting in the minus x direction? We are, right? Here we go. Get this one, put it here. Okay, like that. I'm going to reorder my x hat. Put there. And the next step is to cancel the L. Try to make it as simple as possible. Can I do better than that? I don't think so. Here you go. That's what happens with the electric field when you are at a distance, the left tip of the rod is a distance a from the origin. Okay? Now we're going to do something else. Find an expression for the above E field whenever L, no, it's not L, whenever A is much greater than L. Okay? So suppose that I go ahead and move this rod to the right to a very far away position. This A here, this space is going to increase, increase, increase to a point where A is 10 times L or more. When we do that, the size of the rod is going to be very small compared to the distance to the point here at the origin of the axis, okay? And let's see what happens to that equation. You know, if A is much greater, what it's gonna get? So here you go, we can come up with a nice solution. We can come up with a nice approximation just by doing the same thing that we did before. We factor A. Okay, here you go. I'm gonna factor A right in here. When I factor A, we end up with a 1 on the as a first term and an L divided by A in the second term. Okay? That's the trick that we do whenever we have those terms that are much greater than the other. I'm going to simplify the thing here. I'm going to factor out the A out there to simplify, right? Okay, if A is much greater than L, this term here can disappear, right? This term here disappear. And we can go for our approximation. And we get an approximation that's non-zero. In the other case, we wouldn't get an approximation that was non-zero. Here you go, right in here. Neglecting this term here reduces to what? Reduces to the result of a point charge. Okay? So whenever A is much greater than L, that rod, that finite rod, behaves just like a point charge. Okay? And that's to the zero order approximation. A zero order approximation is pretty good. Okay? In 642, right? We can go to 650. Which one's the next? So that's the one I want to do. Let's see if we can do the other one before. Yeah, let's do the ring now. Annular charge distribution. Okay? Believe it or not, this angular charge distribution is a one-dimensional distribution. And I'm going to explain to you why. What we want to do in this problem is to calculate the electric field of this annular charge distribution at this spot here along the x-axis, okay? Along the x-axis. Here you go. That's the annular charge distribution, radius r. The distance to this charge here is centered at the origin. The distance from the origin to this point is x. Okay. Mathematically speaking, this problem is easier than the other one, but intuitively speaking, it's more difficult. It's more difficult to visualize. Okay? But you have to understand a very important characteristic of this thing. Okay? No matter what charge, what infinitesimal charge you get along this ring, the distance of the infinitesimal charge to this spot here in the x-axis is always going to be the same. Can you picture that? Think about this thing as a cone, right? Think about those vectors here, all those vectors from those infinitesimal charges forming a cone, right? So, because each infinitesimal charge is at the same distance to this point, it's easier to integrate. The problem becomes easier to integrate. That's why I said it's mathematically simpler, but it's intuitively more difficult because now you have to picture the fields here at this spot, right? But if you go ahead and add up the contributions of each infinitesimal charge, what's going to happen? We're going to end up having dE field contributions only along the x-axis because the perpendicular direction, not necessarily y, but a combination of y and z, right? They're going to cancel each other. Make sense? Okay? Net field at this spot is going to be along the x-axis only. And I'm going to illustrate uh, like that. Here you go. A very sick. Oops. This software. I don't like laptops. I prefer desktops. Desktops are much easier to work with. Okay, that's the net field here. The contributions of every infinitesimal charge throughout the ring at that spot. Okay, I'm gonna put it in net. Oh, what happened? Here we go. Mm. Subscript. Oops, subscript. I want. Yeah, now I got it. That would be the net. The question now is how to calculate this net field. This 647. Can we go? Can we? Let's try to use those 3 minutes. Okay. The way to calculate this net field is by calculating this infinitesimal field first, and recognize that it makes an angle phi, right? So it's going to be the sum of the x component of this field, because the y component and the z components are going to cancel out because it's generating a cone in space. Okay? So, 647. You know what? Let's finish here, right? And next time I will do the calculation for you. I will, do the E field of a ring. Derive the E field of a ring. We started. Need to put the. Yeah, we started. You can put the date, right? More. Okay, we started right here. Insert. You go. Save it. Why I didn't save it? Huh. Save it. Yeah, how do I change? He's asking me to save the document online. How do I change it to the hard drive? Do you folks know how to do that? He doesn't allow me to do that. So strange. What do you say? Control F. Yeah, yeah, but if I do Control S, it's gonna save in the on drive in the cloud. Huh? Yeah, let's do that. See? Save as. Huh? Sometimes it doesn't show for some reason. Okay. Let's see. Let's see. Let's see. Yeah. String. Let's see. Is it gonna save to the OneDrive? See, it's on OneDrive. We gotta get out of this thing. We gotta put. Gosh, it's this this thing is such a big mess. I never figured that out yet. I never figured out how to. Desktop maybe. Desktop would work, right? Or maybe this one. I don't know. Well, you're supposed to be saved here in the hard drive. Let's see if it's gonna save now. Already exists. Yeah, hit place. Let's see. Yeah, now I think now it's saving on the hard drive. It's just supposed to be in the on the. Yeah, that's right. Uh huh. Uh huh. Yeah. Yeah, and then just upload it to the. Just upload to the. Okay, so let's stop this thing here before it gets too long.